You know what to do if you hear the beep, right? You just click it again. So last day we looked at correlation, which basically is a measurement of how close are the points that you're looking at to an actual line. So how good would a line be as an estimator of what's going on? Today we're actually going to calculate the line itself. Okay? Oh dear. Alicia, would you mind closing that? Just till they're done banging around out there. So, if I have a situation like this, this is a little artificial, okay? Would you say these lines are tightly clustered, or these points are tightly clustered around a line there? Yeah. So we would say the correlation in this case would be very high, probably be very close to +1. Why +1? Because it's going up, exactly. If it was the exact same picture going downhill, then it would be very close to -1. +1 is perfect correlation, -1 is perfect correlation. -1 just means they're going downhill. +1 means they're going uphill. That is not the slope. The correlation has nothing to do with the slope. It wouldn't matter what the slope was, it's how tightly the points are. So today what we're going to do is actually calculate an equation for that line that most closely matches the data. And so the way it works, it's like this. Whatever the equation of the line is, and we actually usually call it y hat, okay? And the symbols we use, it may feel a little bit backwards. We use B0, B1x. Now, if you remember your algebra, typically how did you write the equation of the line? Do you remember the symbolic notation? mx plus b. You guys remember that? Yeah. Oh, where m was the slope, 0 comma b was the y-intercept. Should I shake his head? This is, I'm not joking, this is probably literally every math class you took from 6th grade on, they do equations of lines. It's funny, it makes it college, even in the pre-calculus classes, they still do equations of lines, even though they do them in pre-algebra, elementary, and intermediate algebra, because they want to make sure everyone has lines. So that was our useful, typical, this is called the slope-intercept form, because I can read the slope, I can read the y-intercept, and I can draw a line really, really simple. Life is good. How do I get this? Well, usually you took points, and then you did the calculation. That's nice. The form of this is a little bit different. This is a little bit different form. It's the same equation. B1 is the slope, because it's the number in front of the x, and B0 is still the y-intercept. But the reason we write it different in stats is, in the higher levels of stats, you may have more than one independent variable. X is the independent variable, it's the input. Y is the output. But in reality, you might have several independent variables. Now remember the problem I talked about last week? I said I was working on a project and we were talking about acceptances to San Diego State and UCSD. You guys remember that conversation? And I said, what were the factors that most highly contributed to success? And it was actually your math scores, your English scores, and negatively, how many hours you were spending watching TV. This was from the 80s and 90s. Now it would be how many hours you spend probably on social media. Same idea. But that's 3 different variables. So that would be saying it's like having an x, y, and a z in the problem. So if you have more than one variable, which in real life you always have more than one variable, you might have an x1, an x2, an x3, an x4. So the equation looks like this because you might have several variables. That's why we write it in this form in statistics. We're doing it with one variable. But in general, in reality, you're probably going to have many variables. And so therefore, the form of the equation, we write it in a little different form, although the meaning is the same. So I need to calculate the slope, and I need to calculate this number based on the information I have. And it's actually not that complicated. The key one here, though, is the slope. As it turns out, now last day, remember, what did we start with? We started with n, the sum of the x's, the sum of the y's, the sum of the x squareds, the sum of the y squareds, the sum of the xy's. Then we calculated the SSX, the SSY, and the SSXY, which basically are the numerators of the variances. Okay, that's what we did last day, and that's your quiz you're turning in on Thursday. A lot of tedious calculations, we got to everything, and then we calculated the regression, the correlation, and the correlation was, if you remember, this over the square root of this. Okay? Now, turns out these three values here also contribute to this. What we get is that B1 ends up being SSXY over SSX. Okay, now, the actual formulas that derive these are not actually derived in statistics. They're actually derived in my linear algebra class, my Math 254. How many remember ever working with a matrix? Remember that in algebra, matrix, vaguely? It turns out the equation for the line and all this is matrix algebra. And we do this in Math 254. It's pretty cool. In statistics, what we have are the summary formulas. We have the final formulas. In the linear algebra class, we actually start from scratch and we derive everything as we go. So we do it a little bit differently, but we get the exact same results. So when I calculate this, I use this value then to figure out what the B0 is. Now here's the one thing. We know there's an X bar and a Y bar also. There's an X bar and a Y bar because I need it in these calculations. So there is an ordered pair on this graph. There is one ordered pair and it's X bar comma Y bar. And let's say it's about right here. Let's say that point right there is X bar comma Y bar. There was no ordered pair from my data that was X bar Y bar. X bar is just the average of all the X's, Y bar is the average of all the Y's. I mean, the chances of them that actually being one of the points I'm looking at, it's pretty unlikely. My line of best fit is going to pass through this value, or this point. So once I calculate the slope, I use this to figure out this. I'll give you an example. If I have the equation y equals, let's say, 3x plus 8, and I give you the point x is 2, can you tell me what y is? What's y? 14. So if I started with this equation and the x was 2, you know y is 14, you go, wow, that was really hard. Yeah, that part is easy. That's not the question. What if instead I said, I have a line, and my line, let me give you a different line. The slope is 5, and the point -1 comma 4 is on the line. The slope is 5, and this point is on the line. Can I figure out the equation of the line? Well, I know it's in the form y equals 5x plus b. The slope is 5, so I don't have to do any work for that part, but I don't know what this is, but I have this point. Oh, so can you put the -1 in for x? Then what would you get? And put the 4 in for y. So I get 4 equals 5 times -1 plus b. Do I now know what b is? What would b be? What would the letter B be? 9. Does everybody see that? Oh, B would be 9. I didn't tell you B, you figured it out. If I know the slope and I know a point on the line, can I figure out the B? Yes, always, easily. So, I have the slope. How do I figure out the rest? Because this point is on this line. So I would have y bar equals b0 plus b1 times x bar. That is an absolute. I know that value. I've calculated that value. I know that value. So therefore, what's b0? It would be y bar minus this, which is exactly what you guys just did over here. So b1 is easy enough to compute. b0 is easy enough to compute because I've already got all that stuff over there. That's the whole point. I've got all that stuff. Okay? Now, what's the point of coming up with a line of best fit? Well, the line of best fit is the line that most closely models the data. There's a couple of assumptions we have to make. First of all, we believe there actually is correlation. Otherwise, we don't even bother with this problem. Agreed? And last day we did the test on correlation. So we have a definite situation where we believe there's a cause and an effect. Secondly, the data has to actually be somewhat linear. Tell me, what do you think if my data looked like this? Would a line of best fit be useful? My data look like that? No, it's not linear. It's going all over the map. So the data actually has to look like it's linear. You with me on that? If it doesn't look like it's linear, then no, we do something else. But if the data essentially looks linear, not perfectly, but essentially it's all moving in the same direction, uphill or downhill, then I'd say, okay, let me first prove that there's correlation, and now let me find the line of best fit. Because now I can use the line of best fit to get conclusions. Okay, we're going to do several examples. But let's suppose, remember the problem we talked about last week with the police running the alcohol tests? And you have a drink, how does that affect your reaction time? And they hundreds and hundreds and hundreds of people, they're having drinks and then they're doing the reaction time. And they find that it's very, very linear. The more alcohol, the greater the reaction time to a stimulus. So with that, and they have all of this data and they see this moves fairly linearly, could they then use that to predict, okay, if you've had this many drinks, this is how long it would take you? Assume, with body weight and all these other things. Yeah, that's why when you get your driver's license, they got that little chart. You've seen it with all the squares that are darkened and lightened and gray. You guys know what I'm talking about? That says if you've had this much, you have had too much, or you're still okay to drive at this point. If you say, well, I had a drink, I waited 5 hours, and then I went and drove, am I going to get a, drunk driving arrest? No, you won't. I had a drink and I waited 5 minutes. Not necessarily, But I had 3 drinks, I waited 10 minutes, and I only weigh 98 pounds. Yeah, I'm probably going to get a drunk driving because it had to do with the reaction time and that sort of thing, because that's what they're measuring there. So the blood alcohol level they're using is telling us where's the safe zone for all human beings? No. But in general, in other words, does everybody fit in the same mold exactly? No, but it's a really good guideline. So we use this to make predictions. Let me give you another simple example. And I did this one last time. Let's suppose that everybody in the class had a midterm score and everybody in class had a final exam score, and that's all you have. And I think I have that on the quiz. Okay? And I found that there was a really good linear relationship between them. And I was able to come up with the line of best fit between them. Okay? Now, Chance couldn't make it to the final exam because, he had a party or something the night before, and it was just, the cleanup was crazy. It took them all day to clean up. If the class had a really tight linear relationship between their midterm and their final, then in theory I could say, well, I can just take his midterm and say, here's what he would have done on the final based on the line of best fit. I mean, literally that's how it's used in real life. I can use it as a predictor. Now, would it be a perfect predictor in general? No, there would probably be a cushion, a plus or minus. What determines the plus or minus? How tight are these points to the line? Right now, would you say these points are pretty close to the line? Yeah, so is the line a pretty good predictor in this example? Yeah, it's an excellent predictor. But what if... Now, same line, but now here's my data points. Is the line a fantastic predictor? No, the points are all over the place. My correlation now just went way down. Yes, they're still moving uphill, but they're kind of all over the map. So is the line a great predictor? No, I can still use it as a predictor, but now my cushion would be humongous. Does that make sense? Humongous cushion. All right, so let's do an example. I'm not even going to give you a situation. I'm just going to give you some ordered pairs to start with, and we're going to come up with the line of best fit. Okay? We'll probably do regression as well. All right, so let's do -4, 11, -2, 7, 0, 6, 3, how about -2, and we'll 1, 2, 3, 4, we'll do one more, and 6, 8. Okay? Sorry, hold on. 6. I'm sorry, 6 -8. Sorry. All right. So I have these 5 data points. And I want to come up with the line of best fit. We might as well do correlation while we're at it because it's all the same calculations. Now, you never have to do this, but it's always a good idea to actually plot the points so that it matches. if my points are going uphill, but my line of best fit is going downhill, that's probably not good. Agreed? If my points are going downhill, my line of best fit has been going uphill, that's probably not good. The equation I come up with ought to match the points. So, sort of loosely, I want to plot these guys. So, let's see, there's 10, negative 10, that's 5. All right. So I've got negative 4, 11, probably about right there. I've got negative 2, 7, maybe about there. I have 0, 6, about there. I have 3, negative 2, probably about there. I have 6, negative 8, probably about there. Whoa, do you know something about my points? I mean, they're definitely going this way, aren't they? So there's some kind of a that way relationship. You agree? So right off the bat, they're probably fairly close to the line. But my correlation, first of all, is negative. That's pretty easy to see. So my line of best fit should have a negative slope. That's one thing I can clearly see from that line. Okay? So let's do all of the summary data. So everyone grab those calculators. So let's do, so my n is 5. Let's do sum of x, sum of the y, sum of the x squareds, sum of the y squareds, sum of the xy's. Let's start with those. So sum of the x's, I see 3, sum of the y's, 8. All right. Did I get those numbers?
The sum of y, I got 14, I don't know if that's right.
18.
I got 14 as well.
4. You got 14, you're right.
Yeah, okay.
You know what, I didn't see the 6. Good, that's why I'm asking you to check. All right. Yeah. So far, so good? Now, this is trivial, this part, but we've got to get these numbers right or the other numbers aren't going to be so good. So, x bar and y bar I need. So x bar is 3 over 5 and y bar is 14 over 5. Because those are terminating decimals, is there any harm in making those into decimals?
No.
No, there's no harm whatsoever. Fractions, decimals aren't going to change anything at this point. But if you have to round it off, leave it as a fraction because that will affect the next calculation, as we know. So now, sum squared of the x's, that's the numerator of the variance. So that's x bar squared minus 5. I'm sorry, sum of the squared, not x bar squared. Minus 5 times x bar squared. And the sum squared of the y's is 274 minus 5 times 14/5 squared. And the sum squared of the xy's is negative 112 minus 5 times 3/5 times 14/5. All right, so let me know when you have numbers for these guys. And it's okay to give me, these are terminating decimals, so you can certainly give decimals in this case. Or you can leave it as fifths, either one. First one is 316 over 5. What's the second one? Anybody? I have that right, over 5 also.
234.8.
So 234.8, so what is that over 5? Read it that way.
46.96.
That's- By the way, you should all be using your fraction key most of the time, so. If you have a terminating decimal, how do you get the numerator? Just multiply it by 5.
1174 over 5.
1174, that's this one?
Yeah.
And what's the third one?
Negative 602 over 5.
Now, I'm gonna tell you one of the reasons you actually wanna leave them as fractions, because when I calculate my slope is gonna be this number divided by this number, and the fifths will cancel. That's one of the reasons fraction is actually convenient, because then that denominator will cancel and I'll get something easier to work with. Now, let's do the regression, keep saying that. Let's do the correlation first. So the correlation is this one over the square root of the other guys. And you notice your numerator is negative, which means your correlation is going to be negative. But that's what we expect, because this thing's running downhill. Now, before you do the calculation, do you think this number is going to be closer to 0 or closer to negative 1? It's kind of a common sense question. 0 means absolutely no correlation whatsoever. Negative 1 means incredibly close, going downhill. What do you think? Closer to 0 or closer to negative 1?
-1.
Probably a lot closer to negative 1. I wouldn't be surprised if we're in the 0.9 something range. That seems, yeah, those points are fairly close together on a line. And the reason I'm doing that before you start, is it possible we make a misentry on our calculator? Particularly when we have 2 different roots in the denominator. Is it possible? Yeah. And so when you get a number on your screen going, no, we just said it's reasonable that we should be in this range. You know, it's an easy, kind of an easy check. I'm guessing we're probably, like Ashad said, we're probably close to negative 1. So if my number on my screen isn't close, I would question it. Remember, correlation is a number between negative 1 and 1. It cannot be outside of that range. Oh, so if I get like negative 6, that's bad. Okay, 5.2, that's bad. 1,000, that's real bad. Does anyone have a number yet?
Negative
Negative.
988.
So that's very close to negative 1. Regardless of whether that's correct or not, is that number reasonable based on what we just said? Yes. So therefore, I would trust it. It's very unlikely you made a misentry and you still have a number that is totally reasonable. Got it? If you make a misentry, you're probably not going to be close. So I would trust that number. This says we have a strong negative correlation. Okay, that's what we did last day. Now let's look for the line of best fit. My slope, I'll write it in words, is equal to the quotient of this over this. Well, obviously the fifths cancel, that's 602 over 316. Does that reduce? Now here's where you use your fraction key. Use your fraction key and put 602, 316 on your fraction key. Well, obviously it will reduce a little because they're both even numbers. But how much will it reduce? I don't know. I'm guessing not much. Now here's where you do not want to do a decimal approximation. You can state your answer using a decimal approximation, but you don't want to use the decimal to do the next calculation. Too much rounding. Probably just 301 over 158. Yeah, I think 301 is probably a prime number. Okay, now how big is that number as a decimal? Now is when I want to do a decimal. I want to, for comparison purposes, I'm going to show you something really cool. As a decimal, that's about what? Negative 1 point. 1.9?
Yeah, 1.905.
Okay, I'll leave it like that, okay? It's about negative 1.9. Why am I doing that? I want to show you something. This is not in the textbooks. This is Mr. Brown demonstrating perfect laziness. I think I did everything right. Are you happy with I think I did everything right, or do you want to know you did everything right? But you're not solving something in general that you can plug back in and check. So how can I check? You're going to love this. Would you agree these are the two most extreme points? They're the furthest ones apart? Now, we know the line does not pass through any points. We just know the line's close to all the points. Let's find the slope between those 2 points. Do you remember how to find slope? It's change in y over change in x. So the change in y would be negative 8 minus 11. The change in x would be 6 minus negative 4. What's that? That's negative 19 over positive 10, which is negative 1.9. The line does not pass through any of the points, but if I found the slope of the most extreme points, I got negative 1.9. What did our calculation just yield for the line of best fit?
Negative 1.9.
Negative 1.905 to be more accurate. Are you happy with that number? You should be ecstatic because I call this the quick and dirty. This is really, really rough. I just took the 2 most furthest points apart and said, what's the slope between those 2 points? That isn't going to be the slope of the line, but it shouldn't be very far from the slope of the line. Do you see why? I just found the slope between these 2 points. So the slope of my line of best fit really shouldn't be terribly different from that number. By the way, when I do this problem, I rarely am this close. Negative 1.9, negative 1.9, no, usually not quite that good. Maybe this would have been negative 2 versus, this is really close. So that means I have tremendous confidence in that. That's what this tells me. Now I want to find the y-intercept part, the b0. Well, I said before, you do that by just simply rearranging. So putting back up, the line of best fit is in this form. Okay, the reason we call it y hat is because it's a sample answer. If I had all of the data points that existed, okay, then I'd be able to tell you the exact line of best fit. I just used 5. Maybe there's infinitely many. I used 5. So this is a sample. And just like everything else, we always have the difference between a sample and a population. This is a sample, so we usually indicate it by this type of notation. So what's y bar? Remember I said y bar equals b0. This is absolute. Therefore, b0 is y bar minus b1 x bar. So what's y bar? 14 fifths. b1, you said, was negative 301 over 158. And then x bar was 3/5. This is our b0. Use your fraction key. It's just so much easier. Unless it's minus minus, so it'll be a plus in the end. And it's all be doing this so we all see if we get the same value. Anybody got something?
I have 623 over 158.
Does anyone else get that?
The same answer.
Okay, that makes me trust it if we 2 of us got the same thing. By the way, now give me a decimal.
3.943.
Okay, so almost 4. It's almost, you all agree? It's almost 4. So my slope is almost -2 and my y-intercept is almost 4. That's that's what it is. So now I can say the line of best fit is that number there. And where's our slope? Minus 308 over 1, or 301 over 158x. So this is the answer. Now, I'm pretty sure I did it right. We already said before, none of these points are going to be on the line. All of these points should be fairly close to the line. So let's just, for example, if I took the y value of 3 on your calculator, excuse me, the x value of 3, replace x with 3. Do this calculation, replace x with 3, and go ahead and give me a decimal value. That's okay. If I replace x with 3, what will I get? Again, none of the points are on the line. All of the points should be close to the line.
You said x is 3?
Yeah, if x were 3, what y value would we get? I don't think that's an answer though, right?
I have negative 1.56.
Does anybody else get that?
I got negative 1.77.
Yeah, that's what it is.
Oh.
177?
1.7.
Okay, roughly close to negative 1.8. On the line itself, there's an ordered pair of 3, comma, roughly negative 1.8.
Okay, I got it.
Look at our input. 3, negative 2. Is that very close to the line? Yeah, it's very close to the line. That's a good thing. None of the points are on the line, but if I input all the x values, I get points that are close. So how can I use this? Let's suppose, and by the way, I've actually seen this done. This is crazy. I've got years and years and years of records, maybe for a particular company. And every year I have, maybe their revenues and things like that. And I found that over a long period of time, it was a very linear progression. But I might have some missing years. So just for fun, could we use the line of best fit to figure out what the y value would be? Let's just say we had a missing input of 4. Could you tell me what the line would have produced if x were 4? In other words, this is your best estimate using the line. You're not guessing, you're saying, no, what would I get on the line? So what would you get? You'd get y hat is 623 over 158 minus 301 over 158 times 4. Now it's totally okay to give a decimal approximation. But you notice we use the fractions because I want absolute correctness. You can always round off your answer. What we tend to not want to do is I don't want to round off, I don't want to round off the actual numbers I use in the calculation. And the fact that they have the same denominator definitely makes it easier to use my calculator. So what would the y value be if x were 4?
Negative 3.67.
Negative 3.67. So that would be, in other words, my best estimation. Now, we're not going to go through and do the confidence interval part. That would be a whole nother lecture. But do you agree then that would make sense to put a cushion on that? To say, now in reality, it should be this plus or minus a little bit? Why plus or minus? Because the points are not all on the line. If every point was on the line, there's no plus or minus. The line is a perfect predictor. But in real life, that is never going to happen. The line is never going to be a perfect predictor. And by the way, in my picture's actually pretty good. I'm going to darken this in a bit. This is the point 0,6. That was one of my data points, agreed? Where's the line crossing? You said it roughly 0,4. 3.94? Oh, can you see it? See, it's crossing 4 units high, even though there was a point of 0.6. So right now the line is below this point, but over here the line's above the point. Over here the line's above the point. Over here the line's below. So the points are on both sides of the line. That's always the case. When we said 3, negative 2, it was very, very close. But the point was slightly above the line. Okay? I think. I could be wrong. Now, The line of best fit is used to basically predict what would happen in a reasonable situation. Now here's one of the things, this is important. My X values ranged from -4 to 6. So I can only use the line to predict things from -4 to 6. I can't use the line to predict things beyond. You say, why not? Doesn't work that way. I'm going to give you a really simple example. How many have ever watched a commercial where they're talking about investments and things like that? I mean, they're always on television, right? And you see them all the time. They're safe. They're not lying to you. And they'll say, you know, we do the investments in your retirement and yada, yada, yada. And then they'll always have information. Well, if you do any research online and you can look and say, wow, last year, this company, you know, the investments earned this much, which is fantastic. But maybe the year before they didn't do so great. Now, what's really interesting is my daughter has a college savings, I don't know what you call it. It's one of these investments that my in-laws set up, you know, when she was a kid. And when the pandemic started, the thing lost like 25% of its value in the first 3 months. That's a lot. 1 year later, it was like 30% above. It went through the roof. It was gaining money. I'd never seen anything earn money like this. So it was great. The start of the pandemic was terrible. The next year and a half. Starting at the beginning of 2022, this thing had almost doubled. Now it's lost almost half its value since beginning of 2022. It's been negative every single month. Now you think, oh, wait a minute, the stock market and all these other areas are doing really well, but this particular set of investments means they made some poor choices. And you can't lose every month because money managers are supposed to move money around and, you know, but this fund has lost a lot of money. Does that mean it's going to continue losing money forever? No. But it's doing a lot of this roller coaster. Is that linear behavior? Not even close. Now, what if? What if over the last 5 years, over the last 10 years, we see a, you know, does anyone here ever do their own investing? Like you like to do the stock market and stuff like that? I had a student last summer, he missed the final exam in one of my classes. I said, what happened? He goes, oh, I do all my own investing. And he goes, I was on a roll and he was up all night and all the next day doing stuff online investing and he missed the final. I hope his stocks did well because he ended up failing the class as a result. But he said, no, I'm doing all my own money management. I'm not joking. He said he literally spent 36 hours straight on the computer because he was on a roll making money left and right. And literally he's like, I don't care about college. It was a Calc 3 class, by the way. It pretty much means he's toast. But you've noticed over the last several years, behavior has been essentially linear. Does that mean tomorrow it's going to continue? No. It doesn't work that way. Tomorrow, it could cave in, just like my daughter's college funds. Tomorrow could be a disaster. When it comes to things like that, you can't use it to predict the future. Now, you can say if it continues to grow at the same rate it has been growing, if it continues, then what is a reasonable projection in the future? You can do that. But you can't say it's going to continue growing. It doesn't work that way. That's why we can, let's just say this did represent some physical, real-life problem. I can't predict what's going to happen in the future. What I can do is take any X values that are in this range and say what Y value would have been produced. That I can do. You have a company that every year you've had essentially linear growth, you know, for 50 years. And so when Lindsay's going back through all the files, you found like 5 or 6 years of missing data. Could you fill in the blanks by using the line of best fit? Absolutely. Is it going to be perfect? No, but the closer the points are to the line, the better that filling in the gap is going to be in terms of accuracy. Has everybody got me on that one? Now, we did an example last day. We talked about BMI. And I did a loose example of height and weight. And we found there was a fairly strong correlation, which there actually is. So if we used that as an example of if everybody in this room, just right now, I said, write down your heights, and we could use centimeters and we could use pounds for weight, it doesn't matter. And then I said, all right, let's use this. Obviously the input would be height. Height can determine weight, weight doesn't determine. Let me put on some pounds, that way I'll grow taller. No, it doesn't work that way. So the input would obviously be height, the output would be weight. And if we found a fairly reasonable linear correlation, then could we predict the weight of somebody at a particular height? Absolutely, that's what the whole BMI thing is. They say a healthy individual, this is what the BMI should be for any individual height. That's how it works. That's why there are tables. But is it a perfect predictor? No, because human beings do not all fall on the same line. Can you think of two people of the same height, but drastically different weights? Can you think, I mean, does that happen? You have two people. You're talking about NFL. You have a wide receiver who's 6'2", 190 pounds, and then you have a defensive end who's 6'2", 320 pounds. Can you have that on the same team? Of course. So is it a perfect predictor if I know the height? No. But we say if we put everybody, all human beings in there, it's a reasonable, and we'd get a cushion, a plus or minus, because people do not all fit on the same line. But we do expect the progression of weight and height to go uphill together. You don't get lighter the taller you are, not in general, okay? And again, I'm not talking human beings in general, I'm saying you. As you got taller, you probably got heavier. I don't think anybody here, said, well, when I went through my growth spurt, I lost 50 pounds. I don't think it usually works that way. Maybe you gained 50 pounds. Let's do one more of these. And I'm going to do does anybody have the problem that we did last day? I did a height and weight problem, just to save ourselves some time. Well, we did with all the summary data. Does anybody have it in the notes right here?
Yes.
I'd like to save some time. Do you have it, Ashad?
Yeah, I have it.
Can I borrow yours for a moment?
Totes.
This is a problem we did last day. Oh, beautiful. This is a problem that we did last day. And we said we had 6 individuals, and we had their height in inches and their weight in pounds. And this is what we had. That was me, by the way. Okay, then what we did all of the summary data. We did all of these things. And so the ones that I need the most for the next part of the calculation was, we got X bar was 405 over 6. We got Y bar was, I think that's 994 over 6. We got SSX was 27,529 minus 6 times 67.5. Oh, actually, I'll use the fractions, because I would like to maintain the fractions as long as we can. 405 over 6 squared. Again, I'm skipping all the little pieces because we already did the calculations last day. We have all this information. 172,774 minus 6 times 994 over 6 squared, and perfect. All right. Thank you, Rashad. All right, so now what we want to do, since we did this problem last day, we calculated the correlation coefficient, the R, and then we determined if it was reasonable to say that there was correlation. We said absolutely, it was very strong, our t-value. Today, now I want to take the exact same information and I want to come up with the line of best fit. Now, do you suppose this data is perfectly linear? I mean, look at this. This person is 11 inches taller, but they're 105 pounds heavier. Okay, but this person here is 2 inches taller than this person, but they're 34 pounds lighter. Is this perfect linear correlation? Of course not. But clearly, as you get taller, you get heavier overall, but it's certainly not going to be on a line. I mean, obviously, these two things alone tell me it's not perfect. So now, let's start by calculating B1. So B1 will be, if you can give me a value, this would be useful. If you could tell me how many 6. So with your calculator, Each of these are gonna be something over 6, but those will not be terminating decimals in general.
Can you use the thermometer, please?
Oh my God. You have all the stuff on your notes, don't you?
Yeah.
All right, so take a moment, give me the fractions in each case, because none of these are gonna be terminating decimals. This is gonna be this. In fact, let me go like this.
What do you say you have to do for that? You multiply it by,
Yeah, go ahead and calculate this, but leave it as a fraction. So go ahead and use the fraction key on your calculator. Everyone do that for just a moment. All right, do we have values yet? Yeah, sometimes the numbers are so big your calculator won't be able to preserve the fraction, but because my denominators are so small, here's a simple way to cheat. This is what I do. Do the whole thing on your calculator, you have a decimal value, but your answer is something over 6. So just multiply that decimal by 6 and now you have your numerator. That's the simple way of doing it. It's cheating, but it's easy and it always works. Okay, so what do we got? Maybe got the first one yet?
6, oh, no, that number, 1149.
So 1149 over 6? Does anyone else have that?
Yeah.
Yeah? Okay, what's the next one? Again, you can do the whole thing and then just multiply your answer by 6, and that gives you your numerator, because you already know your denominator.
Do we need that value?
48,607.8.
No, you can't get a decimal.
Okay.
It's not possible to get a decimal in the numerator. Look, this is,
48.
if A over B equals C, then A equals B times C. You do the whole quotient, you get a decimal. Multiply by 6, and now you get the integer numerator. This actually is a process that should take only a few seconds. This can't take minutes. A cheap calculator from beginning to end is probably 10 seconds. But you're making it really complicated if you're not getting the answer immediately. It's something over 6, get the decimal, multiply it by 6, and that's your numerator. That's it. It's that easy. If you don't want to use your fraction key, there's a way of doing this in about 10 seconds. I just showed you. So I'm worried that you're struggling now. This is on the final exam. This is a question and you have to do it this way or you can't get the right answer. I want you to get the right answer.
We got 48608.
48608. And then the last one?
6774.
6774. Okay, now, B1 is this guy, 6774, over this guy, 1149. Now, obviously, the sixths cancel, and I get 6774 over 1149. Now, I have no idea if this reduces or not. So how do I tell? Now use your fraction key. It will reduce. Maybe not. I think it will reduce. Because numerator and denominator are both multiples of 3, so I know it'll reduce a little bit.
2258, 38 over 383,
2258 over
383.
380. Well, that's a little better. I mean, it's not wonderful. So, what does that mean for our answer over here? It means our answer over here now I need to figure out what goes there. Now I go back to the x bar and the y bar, like we did before. So again, if all else fails, remember if y bar equals b0 plus b1x, then b0 is y bar minus b1, y bar, sorry. So, I'm going to take my y bar, which was 999.6. This is going to be exactly like the calculation we just did a moment ago, by the way. So my b0 is 994 over 6 minus this number, 2258 over 383 times 405 over 6. Okay? Now again, use your fraction key. It's probably going to be something quite large.
Should it be a fraction?
Well, hopefully, is it giving you a decimal?
Yeah.
All right, multiply your screen by 383. Does it give you an integer or a decimal?
I
Decimal.
got this.
Is it a terminating decimal?
No.
What does it look like?
Negative
Well, the decimal part.
66667. 66.
Okay, so that means there's an additional 3 in there. So multiply by another 3. Multiply by another 3, and that means the decimal that you just had on your screen, multiply that one by 3.
Okay, I have negative 266894.
2,
66894.
does anyone else get that?
What, negative 287144?
I don't know what you just did.
I don't know.
No, I don't know. He was just telling me. It was like a
Do you-
rabbit hole.
Well, just do this.
I'll just do that.
Do this and get the decimal. That's all I'm saying. Do that and get the decimal.
I have that.
Now, because you got a 0.666, that meant your answer was n thirds. So 383 wasn't the common denominator. It was 383 times 3 was the common denominator, which was back to our 1149. So do that whole thing on your screen, and then multiply your screen by 1149, and tell me if you get the same number. You guys had numbers that were very far apart. I'm wondering if one of you added when the other subtracted. That's the thing. Because I believe the answer should be a large negative. Did you get a large negative, Lindsay?
Yeah.
Did you get the same
I'm
numerator?
confused now.
Okay. This is a decimal with a not terminating decimal place,
Yeah.
but you know the denominator.
Now I do have it as a terminating decimal.
What do you have now?
I have negative 232.283725.
That's what I'm gonna,
Yeah.
Yeah, I got that.
I got that too.
You got the first one?
Yeah.
I got it.
If I do this, I get something ugly. We know that 383 is going to work. This reduces to thirds. This reduces to halves. And then when I multiply that, the halves will cancel. So I know the final denominator is going to be 3 times this. I know that. I'm just trying to get you guys to see how you can mess around with your calculator without doing any algebra. Just use your calculator to give you the same answer. So the common denominator, when I'm all done with this, that should be my denominator. I got it. Now here's the problem we have. The numbers are too big for a lot of your calculators to store. All calculators have a limit when you want to do a fraction. Most calculators won't go past 5 digits over 5 digits. It's too big of a number to store, so it changes everything to a decimal. My numerator is humongous, wouldn't you agree? But I wanted that because when I enter a number, my final answer I want to be a decimal. Sometimes these numbers are so big that you can't even get the fraction. You're stuck with the decimal. That happens. That's real life. It's just that if we can get away with keeping and preserving the fractions, it definitely makes the calculations more accurate in the long run. So now, this is the equation that governs this group of people. So, somebody comes along and they are exactly 6 feet tall. Can you tell me how much they should weigh according to our group? According to this group, not according to all human beings. Where do they fall on the line of best fit? So what am I going to use for their height?
6. 6 feet.
So how tall is 6 feet?
72 inches.
72 inches. Yeah, I really can't use 6. That'd be 6 inches tall. So all those heights are in inches. So what do I do with the 72? I put it right here. And now you can go ahead and leave these as a decimal. So enter this number plus this number times 72, and let's see where that gets us. Now, I'm guessing that person's probably going to be, in the high hundreds, maybe even close to 200 pounds. That's what I'm guessing based on those numbers. Again, in real life, if it's not convenient to keep the fractions, you can use decimals, but the problem is you get decimal round off. There are times when you do your calculation, you should get a nice happy integer answer, but you don't get an integer because of the prior round offs. Anybody got a number? What's your number?
192.
192?
Yeah.
So, does anybody else get 192? So here's what we're saying. Here's a group of people that as they get taller, clearly are getting heavier, but it's not a perfect line. It's not a perfect line. This person's 6'1" and weighs 221 pounds. This person's 6'3" and only weighs 187. So taller means heavier, but not perfectly. All right? This person's taller than this person, but weighs less. 6 inches shorter, but only 7 pounds lighter. So it's not perfect, but there's clearly a trend. So we say, based on that trend, if somebody is 6 feet tall, then what is a reasonable weight considering our group? Does that make sense? And you just said 192 pounds is a reasonable weight for this group. Now, in reality, we probably want a cushion. We probably want a plus or minus. But that wouldn't surprise us, if somebody was in that neighborhood. Okay, that's where you're using the line of best fit to now answer a question. You told me the line of best fit, but what's the point of having this information? Because now you can give me different heights. How about a person who's 5 feet tall? You said 6 foot tall should be about 192 pounds. So how about 5 feet tall? We're talking adults, people who are done growing, basically. Height-wise, not sideways growing, vertical growing. So what should a 5 foot tall person be? How many inches? 5 foot tall is how many inches?
It was 60,
60.
maybe 121 pounds.
About 121 pounds? Is that reasonable? Well, check this out, guys. This person right here is 4'11", but they weighed 122 pounds. This person's 5'2", and they actually weigh a little less at 116. You said 5 foot tall came in about a 121. Is that pretty accurate based on those? Yeah. Literally, it was the average of those people, wasn't it? So this can be used. Now, is this perfect science? Well, no, because it's not a perfect relationship. But is it a reasonable starting point? Yeah, now this is why last day I used BMI. I'm one of these people that think that's absolute utter BS personally. I find it very offensive that, I'm told that I'm grossly obese because my BMI is high. Even though if I lost 10 pounds, you'd see my ribs sticking out, But the thing is it's a good starting point, but the problem is it's not a line of best fit, it's like a band of best fit. The variation is huge. At a particular height, a healthy individual has a tremendous range of weights. But they're saying, there is sort of a middle ground that most people would fall into at a particular height. And that's kind of what it means. So if you were exactly 6 feet tall, is there a weight you're supposed to be? No, it depends on your body type, doesn't it? Could you be really skinny or really heavy at 6 feet and in both cases be really healthy? Yes. Could you be really skinny or really heavy and in both cases be really unhealthy? Yes. But is there sort of an average that most people that are 6 feet tall kind of fall into? Yes. And that's why we're using this as a starting point. Not necessarily a guideline, like you have to be this way. Because if you go to the doctor's office and you have your physical, that's exactly what they're going to do. The very first thing they do at your doctor's office. Anybody have a physical recently? It's the very first thing they do.
Blood pressure?
Even before that.
Oh, temperature.
Take your weight.
Oh, really?
Sometimes they measure your height. But they always, the very first thing they always do, even when you're little kids, first thing they do, they weigh you. Hopefully they do your height too. Then they go in the room and they do your blood pressure and all that stuff. But they weigh you. It's the very first thing. Why? Because then they can quickly calculate the BMI and that kind of stuff. So they have that information before you even start, way before the doctor gets there. Because now they have something to start with. It's not an end all. It doesn't mean if you are a certain number, this is good, this is bad. This is just a guideline. And it's also a comparison to them the last time you were in. That's also a good thing too. All right, let's go ahead and stop that. All right, we are now